Good evening, everyone. Thanks for the introduction. I'm Francesco Daghero, third year PhD student at DAUIN, as said. And in this presentation, I'll try to introduce you to my research in a fast, obviously, way. Not everything will fit, but I hope I'll give you an idea of what my day-to-day research life includes. And so, without further ado, let's dive into it. My research topic can be summarized as machine learning, applying machine learning in smart sensor. Is a PhD that is funded by ST Microelectronics, and the whole idea is moving from a cloud-centric approach where we have the sensor deployed, the IoT device that collects the data, transmits the data to a server where the machine learning model is deployed. The machine learning model performs its computation, its inference, and sends back the result. Okay, we want to move towards an edge computing approach where we move the machine learning model as close as possible to the source where the data is collected. Why we want to do this? It's because we drop the need for a constant internet connection, an internet connection that may be congested, that may be unreachable, that may be unsecure. And so this edge computing approach allows us to reach lower latency or more predictable latencies, higher energy efficiency, higher security, but there is a catch, in the sense that cloud machine learning models are designed for the cloud. They will not, we will not be able to directly deploy them on ultra-low power devices, memory constrained IoT devices, because they are just too computationally intensive and too large. And so my research activity falls in a branch of machine learning that is called TinyML, Tiny Machine Learning. That denotes the set of techniques of models that are tailored for a deployment at the edge, with the goal of reducing as much as possible the inference or the training cost in terms of memory or energy footprint, trading off as little accuracy as possible. And my work mainly focuses on optimizing the inference for ultra-low power devices such as microcontrollers. And what we usually work on is starting from efficient models, efficient machine learning models, going to runtime optimization such as the adaptive inference, or static optimization such as quantization. All of them, I will introduce them in my presentation. And actually in this presentation I introduced two of my works, of my research work, with the first being actually the sum of all the 3 points that I've just listed, as it's focusing on tree-based ensemble, such as random forest, gradient boosted trees. These are very popular models, but why are they popular for embedded tasks? The reason is that they are accurate, and often comparable to deep learning models, and they require low memory and computational footprints when we have small ensembles, because everything changes when you try to deploy larger or deeper tree-based ensembles. In this case, their footprints grows rapidly, maybe linearly or even worse. So in literature, what we find currently is that multiple works focus on optimization tailored for high-end hardware, for GPUs, for instance, parallelizing their inference to achieve, to reduce latency. However, this optimization do not translate well, or at all, on ultra-low power devices. Again, microcontrollers is the example here. So what we do is we start from scratch. We start from the basic implementation. How do we want to represent our tree in C? That is called, and we want an efficient data structure. So the first thing is moving toward an array-based representation. You think it as the nodes is an array of C-like structures where we store the index of the feature, where we split the threshold, the value of the threshold of the splitting condition, and the shift required to reach the right child. The first thing that you may notice that we don't store any pointer or index or shift to the left child. The reason is that by storing the nodes in a pre-order way, the left child is always consecutive in the node array, so we don't need to store its index. However, what we may notice here in the leaves array is that we store the full set of probabilities. This is different from other common implementation for embedded targets, because they generally store only the most likely class, not all the set of probabilities. Why we do this? This is obviously a memory overhead, but we do this because that's bring us to higher accuracy. When we are accumulating, when we are merging probabilities from multiple trees, this boosts our accuracy, and furthermore allows us to estimate the confidence of our prediction, because we know that if the logits, if the probabilities are all similar, the confidence of our prediction is not so good. The classifier is unsure about its prediction, and this allows us to leverage the adaptive inference that I'll introduce in a pair of slides. Another contribution here is the quantization, a static optimization that is very popular for deep learning models, but far less explored for tree-based ensembles, actually. And in this case, we use a symmetric max quantizer to quantize both inputs and those thresholds and leaves probabilities. And we achieve memory reduction in memory and faster inference when we accumulate the logits. The idea is that we can do this quantization both pre-training and post-training for the inputs, and for the probabilities we just do it post-training, since the output range of the ensemble is known. Another optimization that we explore is the memory hierarchy. We can, in some microcontrollers, we can select where we store the data structure, whether we store them in L1 or in L2. Well, that's not trivial, because the different access ratio, the speed of access changes depending on the storing in L1 and L2, so we need to optimize this. And in this case, it's, we use a knapsack algorithm where the weight of each array is their size, and the value of storing in L1 each array is the number of times we access them during the inference. And this allows us generally to store, inputs and outputs and roots in L1, while the others in L2, because they're generally too large as well for L1. But the most interesting part probably is the adaptive inference, which is probably the core of my PhD research. Okay, the idea here of the adaptive inference is that not all the inputs for machine learning models are equally complex to classify. There are some very easy inputs, think to a very crystal clear image where the target is very well recognizable. Well, that's an easy input. That's not a blurry image where it's difficult to tell where the target that we want to recognize is. In this case for trees, maybe for signals. But the idea is that all the inputs require a different complexity. For easy inputs, we have that all our 100 trees in the ensemble all predict the same thing. So do we really need 100 trees that predict the same things, or we are just wasting energy, which is very precious for embedded targets? But okay, the idea would be then, let's just shrink the ensemble. Let's remove the trees that we deem unnecessary. But at that point, all the hard inputs, which are less, obviously, but still they are there, will be immediately all misclassified, because we are reducing the predictive capability of our ensemble. And so we would ideally need an approach to decide at runtime how many trees we want to execute. And this is the base idea of the adaptive inference, adapting the computations depending on the difficulty of the input. So how do we do it? It's that we run a subset of our ensemble, a batch of trees, that may be 4, 1, as we prefer, and then we accumulate their predictions, and on their partial predictions, we run a block that is called prediction confidence evaluation, that is telling us the confidence is higher than a user-defined threshold. Yes. Okay, high confidence, we stop the execution. No, it's not confident enough. We keep going with the following batch until we reach the same prediction of the static ensemble. We run out of batches. And as you can imagine, the core here is the prediction confidence evaluation that must be very accurate, but not too computationally intensive. Otherwise, we overshadow any gain in terms of latency. And we estimate, we actually benchmark several approaches in this work that are based on the logits. some results. The first are on quantization. As you can see here, I'm showing the results of several ensembles. Each point is an ensemble trained with different number of trees and different depth. I'm benchmarking two tree-based ensembles, a gradient boosting trees on the left and a random forest on the right, and two types of data, EMG-based dataset and activity recognition based on inertial sensors. And the point is that we can see here that 32 bits are rarely necessary. Instead, actually, the regularization effect of quantization boosts our performances and allows us to get better results with 8-bit or 16 bits. The difference is depending on the type of the tree-based ensemble. GBTs require more logics as they store the residual errors in the leaves. Another set of results is on the adaptive approach. Here you can see each blue point is a different static ensemble, requiring a different deployment step. The red points instead come from only one ensemble, changing the threshold that I mentioned before that's telling us the confidence, the prediction confidence is high enough, and so we can trigger the early stop. So changing the threshold at runtime without any additional deployment, we can spawn different points, Pareto optimal points, that actually perform even better than the static models. And in this case, we deploy it on a RISC-V SoC, GAP8, and we can see that we obtain a cycle reduction at ISO accuracy of up to 30%. The second work that I introduced, this work has been published, and you can find here the link and the DOI, and the code has been released as open source to deploy these efficient tree-based ensembles. The second work is again on adaptive inference, but in this case we start from another consideration, that is not all the classes are equally complex to be classified. So we have that the easy classes generally are the most common. The complex classes are few, but again we cannot just shrink statically the model, otherwise we will misclassify all the complex classes. And so what we propose in this work is implementing a hierarchical approach where we deploy first we deploy two models, a decision tree and a convolutional neural network. The decision tree is trained only on the easy classes and on a fallback class that merges all the other classes that are not the easy ones. And at runtime, it will tell us it's this class, an easy one, another easy one, or a fallback class. If we predict the fallback class, in that case, we will activate the convolutional neural network that has been trained on only on the complex classes, and we'll perform our prediction as well on the convolutional neural network. So the idea is that since the easy classes are the most common, most of the time we will stop at the decision tree. But for the complex inputs, for the complex classes, we will still use the convolutional neural network, thus without losing accuracy. And here you have the results. In this case, we achieve with our approach, with our adaptive hierarchical approach, a more accurate model with a smaller for the same accuracy, up to 64%, and more energy efficient for the same accuracy, up to 31.6%. And this work has been published as well. Here you can find the link. And this concludes my presentation. Thanks for listening. If you have any questions.